All right, so we're going to look at something that's really kind of cool that we can use to find volumes. Okay. Now you've learned back in geometry how to find volumes of, say, a cylinder or a rectangular prism,
SAT even gives
or
us
other
a
things.
formula bank for them.
Yeah, you even get some formulas there. Okay.
I don't have to do this.
But
Except for the SAT.
here's the thing, okay? Here's the thing. Most stuff in life is not this nice rectangular prism or this nice perfect cylinder.
This got really depressing.
Okay? Well, here we have something that is kind of cylindrical, but it's not a consistent cylinder. It's not the exact same. It's not the exact same size on both ends. You know, in this nice perfect cylinder like a pipe or something. Here we have something kind of looks like I don't know, a lampshade or a megaphone or something like that.
Or tears.
Okay? Tears. You're so depressed.
Well, you just told us that not everything in life is going to go good.
Oh boy. All right. So, what I want to do though is I want us to develop a formula for being able to work with these things, okay? Let's start with the volume of a cylinder. The volume of a cylinder is the area of the base times the height, okay? And by the way, that works for prisms as well. That's why I use that instead of a more specific formula, okay? But for a cylinder, the area of a base, the base is a circle, right? So your circle has an area of what? No, just a circle. There we go. Pi r squared. Okay, pi r squared. H. All right?
Yeah.
Now, here's what we're doing, okay? I want to draw this here, and then we can make some connections to other functions. Let's say I have a cylinder where I'm going to take the circular part, okay, and center it on the x-axis here, okay? And then, so let's say it's wrapping around there, and let's say it goes down to this length right here, okay? So it's going to be the same height above and below.
We're doing the area of the cylinder and then putting a triangle on top of it.
Okay, not exactly.
Good.
But what we have here with our cylinder, okay, you guys know that this would be the radius, okay? This would be the radius, and the distance between where we started and this side, so the distance between those bases is your height. Okay, that's the height. So we do pi r squared h. All right, does that make sense? Now, let's think of this in terms of a function. Okay, in terms of a function, we have, let's say just this line, r, or y equals r, and we are going to revolve this around the x-axis 360 degrees. Okay? So we took this line and we just revolved it around, and that's going to make the outside shell of our cylinder. Okay? So our function is f of x equals r. Now, let's think back to when we started with our integrals. We approximated area under a curve by cutting it into little rectangles, right? So if I took this, and let's say I cut it into rectangles like this, okay, then each of these segments has a different area, okay? the height of that segment would be r, and the width of it would be whatever the distance between these two ends is divided by the number of rectangles I have, okay? Now, let's say that we take that area and revolve it around. So it is a perfect cylinder, okay? I'm going to call that difference there my dx. Alright, I cut it into separate pieces. Remember we said the width of the rectangles was our dx, okay? If I just looked at this cylinder here, this little one, okay, its radius would still be r, and the area of the base would be pi r squared, okay? But then I would need to multiply, sorry, I have too many r's in there. I would have pi r squared, but then its width would be dx, right? So that would be the volume of one of those rectangles. Okay? Now, to find the volume of the whole cylinder, I would need to add up all of the different rectangles, right? But then to get a more accurate representation of that, I would take the limit as the number of rectangles approached infinity, right? You guys remember doing that? No. Okay. We made those little slivers more and more narrow to get a more accurate representation. Okay? Well, what is the limit as n approaches infinity of the sum? Integral. That was our definition of what an integral was. So guess what? We have the integral of pi r squared dx. Okay? Now, let's extend this. Now, come on, this part is not hard. Okay? Our function was just the horizontal line r. Okay? Pi r was the f of x, right? So if we apply it like that, guess what we now have? We have the volume, where we're finding volume. We have the volume even if r is not constant. Whatever the function is, our radius is going to be the value of that function at that point. So our radius of these little slivers is changing depending on what x was. Just like when we did the rectangles before, the heights of your rectangles was changing according to f of x. Okay? So
Probably be like an exponential function.
exactly, okay? So let's look back up here at this thing, okay? You'll notice, let me zoom in here real quick. You'll notice right here, the radius is whatever f of a is. That's our radius at that moment. Over here though, let's say that this is the point C on the x-axis. The radius would be whatever f of c is. And over here at the end, the radius is whatever f of b is. Okay? So notice our radius is changing, but if we're looking at our volume in terms of this integral, it doesn't matter if the radius is changing. Okay? Now, the only thing what we're missing here is the fact that we started at a and we ended at b, so this is actually a definite integral from a to b. And that right there is the formula for volume of a solid formed by revolving a function around the x-axis. Okay?
So the f of x squared, pi of the f of x squared is always going to be the same for whatever we have in there.
Yeah. That's like your pi r squared.
So for the cylinders, but what if are they all going to be cylinders, what we're going to do?
Well, they're all going to be cylindrical because we're revolving it around the x-axis. So even though the thing itself may not be like rounded or whatever, when you revolve it around the x-axis, you can treat them as an infinite number of minuscule cylinders.
So the only thing that will change will be like what you plug in for the f of x and the a and b, right?
Yeah, yeah, that's right.
It could be like a quadratic or.
Okay, so let's like make some connections here. This right here is the area of your base, okay? And the b minus a and the dx is like your height, okay? So base times height. All right. So let's actually take a look at an example here. Now here, instead of using f of x, they used y, which is fine. And also notice since pi is a constant, you can pull that out in front. Okay? You pull that out in front. So here we have a region is enclosed by y equals f of x, the x-axis, and the vertical lines x equals a and x equals b. And it's revolved through 2 pi, or that's revolved all the way around in a full circle about the x-axis to generate a solid. Then the volume of the solid is given by our formula, pi times the integral from a to b of y squared dx. Okay, so that's just a restatement of the formula we just developed. Okay? So let's actually try this one. Alright, here's the volume of a solid, and our function, we start out with kind of an easy one here. Our function is just the line y equals x. And we're going to generate this when x equals 1 to 4. Okay? So we have here the integral. We're going from 1 to 4. So our lower bound is 1, our upper bound is 4. Okay? And it's pi times the function. So in this case, the function is just x squared dx. Okay? Well,
the dx is next to the x squared, right?
It's after the x squared, yeah. Okay. So now integrating this is pretty easy. It's just pi x cubed over 3. And we're going to evaluate this from 1 to 4. Okay? So here we're finding our velocity, or not velocity, our volume. Okay? So let's see, 4 cubed is 64 over 3 is 21 1/3 pi.
Can we leave it in terms of pi?
Yes.
Okay.
And mistakes, why is it x squared again?
Because it's the function squared. Remember our formula, the area of the base was pi r squared. So it's pi times the function squared. Okay, so we've got 21 1/3 pi minus 1/3 pi. This is just 21 pi. And we don't have units here, but these would be cubic units because it's volume. Let's try another one here, okay? And let's actually sketch this so we'll actually know what it's looking like. We have the volume of a solid formed when the graph of the function y equals x squared for x equals 0 to 5 is resolved through 2 pi about the x-axis. So here we have our parabola. And at 5, we have the point 525. Okay? So this is the shape that we're going to revolve around the x-axis, this kind of fan-looking thing. And then after we revolve it, it's going to look something like this. Kind of like one of those old, kind of like one of those old record player megaphones or something. Okay. But go ahead and try to set this up and figure out what the volume would be. Alright, so setting this up, integral from 0 to 5 of pi x squared squared dx, or you have to square the function, is the integral of pi x to the 4th dx.
So, when we're integrating it, if, for example, instead of being just x squared, it was 1/2 x squared, then we have to do 1 over a as well.
If it were 1/2 parentheses x squared,
Yeah.
yes. 1/2 x in parentheses squared.
Yeah.
Or you could just simplify the 1/2 squared first, and
Right.
that would might be easier.
Mhm.
Okay. All right. So our integral's pi x to the 5th over 5. We're going to evaluate it from 0 to 5. When you plug in 0, you get nothing. So it's just 5 to the 5th pi minus 0. And 5 to the 5th would be 3125.
It's 5 to the 5th pi
Yeah.
divided by 5.
Divided by 5, so it's 625 pi.
Oh yeah, divided by 5. I lost my divided by 5. So yeah, so that divided by 5 is 625 pi.
Is the area.
And that's
That's cubic,
cubic
or volume
units.
cubic.
Yeah, it's a volume, so it's cubic units here.
You will take points off if you won't state the units, right?
Actually, they do not take off if you don't list units, as long as they didn't like ask for the units or something like that. So yeah, on the exam you don't have to bother with units. It is a good habit to get into though, just practically though. Alright, so let's look at one other example. Let's say that we have a shape of a radical function like this. Okay? And so this is y equals square root of x. I'm going to start at 0, and I want the volume, let's say I want the volume to equal 10 cubic units. Okay? We can find the volume and find out how long we should cut this thing by taking the integral from 0 to, say, b of pi times the square root of x squared dx, and then setting that equal to 10. Okay? And notice now, if we were designing something and we wanted it to hold 10 cubic units, we would know how long we needed to make this thing in order to hold exactly what we wanted it to hold, by solving the integral first, setting it equal to 10, and then solving for b. Okay? So that's one of the applications here, and this is how they design things to be able to hold a certain amount. Okay? Now, a computer might do a lot for the person designing it, but this is what's going on there. So if we simplify, we get from 0 to b of pi times x dx. That's going to be pi x squared over 2 from 0 to b, which equals pi b squared over 2 minus 0, and then that needs to equal 10. So we solve this and we get b squared equal to 20 over pi, and so therefore b is the square root of 20 over pi, which is 2.523. So we know if we were to cut this thing off right here at 2.523, it would hold, once we revolve this around the x-axis and made this bowl shape, this bowl would hold 10 cubic units of whatever we wanted. So that's just one application of these solids of revolution.